the ethoxides, we have used the range of carbon-13 labeled ethoxides, a set of deuterated ethoxides, and we have replaced the methyl N group with a fully fluorinated methyl group. The chemistry under discussion here is the catalytic oxidation of alcohols to aldehydes. It's known to, copper is a good catalyst for this. It shows some selectivity in that it tends to leave the CO bond intact. This chemistry is very well understood by UHV surface science. And here I've shown it for ethanols and fluoroethanols, but it's completely general for short-chained alcohols, where on the clean copper surface, the alcohols adsorb and desorb reversibly and molecularly, monolayer desorption complete below 200 Kelvin. On the pre-oxidized copper surface, which is formed by exposing the clean copper surface at 600 degrees Kelvin to high background exposures of molecular oxygen, on that surface, the alcohols deprotonate. Below 250 Kelvin, water is desorbed, leaving the stable adsorbed alkoxide intermediate. That's the subject under discussion this afternoon. Upon further heating, this species undergoes beta hydride elimination. One of the hydrogens is lost to the surface. The double bond forms between the carbon and the oxygen, and this species desorbs as the aldehyde. I'd like to show you now the experimental conditions for all the spectra I'll be presenting. The multilayer alcohol spectra are all about 20 monolayers of the alcohol as judged by the exposure. Exposed at the crystal at 100 degrees Kelvin. The spectra are taken at 100 degrees Kelvin. They are 1,500 scans at 4 wavelength resolution, about 12 to 13 minutes data acquisition time. The ethoxide spectra are all, the ethoxides are all formed in exactly the same way. That's the pre-exposure 32 lang-meters of molecular oxygen with a crystal at 600 Kelvin, and then direct capillary array dose of the 0.1 lang-meter of the ethanol with crystal at 250 Kelvin. This produces a saturation coverage of the ethoxide as determined by the subsequent aldehyde yield during a temperature program reaction rate. The spectra are 5,000 scans of the sample at 4 wavelength resolution, data acquisition time of about 24 minutes, and the crystal is at 100 Kelvin. Now, surface vibrational spectra of alkoxides have been taken before, initially, and still quite often in UHV, by electron energy loss. And in those spectra, for the skeletal stretches, they usually identify 2 modes. They are around 850 and then around just below 1100. And those 2 modes are associated with the normal local groups, carbon-carbon, carbon-oxygen, carbon-carbon being a lower frequency. Here I show the 4 spectra of the carbon-13 labeled ethoxides. The unlabeled ethoxide here, labeled in the methylene group, then in the methyl group, and here the doubly labeled ethoxide. In the region between 800 and 1300 wave numbers where you find the skeletal stretches. These spectra show first that there are, in fact, or for the infrared spectra, there are 3 absorptions. The interesting thing about those 3 absorptions are that they are essentially unchanged from the positions for these modes in the ethanol, whether it's gas, liquid phase, solution phase, or crystal phase ethanol. So apparently, we can describe these skeletal stretches as they are described in ethanol. That is, that the loss of the OH mode doesn't grossly affect the internal structure of the rest of the species. And even putting that ethoxide down on the surface doesn't grossly affect the dipoles associated with the skeletal stretches. When we do that, we find that we would assign these modes in terms of a symmetric and asymmetric CCO stretch, and a third normal mode of vibration that involves the CO stretch and the in-plane rock and methyl group. But in order to really determine whether or not this is an adequate description, we have undertaken to take these spectra of the carbon-13 labeled ethoxides to determine whether or not their shifts, their frequency shifts, coincide with the motions we expect from these normal modes. And it's easier to see when it's tabulated, as I've done here, where I show for each of those 3 skeletal stretch modes the frequency shift upon labeling, and for each of the labeled ethoxides, the shifts are reported as shifts from the frequency of the unlabeled ethoxide for that mode. The first indication that the atoms are more intimately mixed than could be described by the discrete carbon-carbon and carbon-oxygen modes is the fact that for each of the three skeletal stretch modes, the greatest shift is for the doubly labeled ethoxide. But more particularly, here outlined in blue, the mode which would otherwise be described as the carbon-carbon stretch, you find that labeling across that carbon-carbon bond gives an unequal shift, which would have to be explained by asymmetry somehow. But the more definitive proof here in red, if you label just the methyl group, then you find that the shift is the same for these two modes. And that would not be the case if they were discrete carbon-carbon, carbon-oxygen modes. Of course, since one is involved, the methyl group is involved in the carbon-carbon stretch, but not in the carbon-oxygen stretch at all. The description as, in terms of symmetric and asymmetric CCO stretch, is borne out, even does explain the very large shift upon labeling the methylene group for this mode here, the asymmetric mode, in that carbon in the asymmetric mode undergoes a very large amplitude of displacement, somewhat transverse to the sum of vectors along the displacements along the carbon-carbon and carbon-oxygen bonds. It also, these data bear out the description of that third normal mode in terms of a CO stretch in an in-plane rock, in that labeling either the methyl or the methylene group gives a stretch, a frequency shift, and the frequency shift is larger for the methylene group, which corresponds to a larger amplitude of displacement of the carbon in the carbon-oxygen stretch as opposed to a carbon in an in-plane rock. For the alcohol, the ethanol, and ethoxide itself, then, here are the spectra of, on top, the multilayer ethanol, and on bottom, ethoxide saturation coverage on the copper 111 surface. I've identified many of the modes and colored some of them in for viewing. You can see here in green and red the symmetric and asymmetric CCO stretches. In the higher frequency region, find the alcoholic OH stretch here. In blue, we can identify the asymmetric methyl group stretch. And then below that fairly diffuse region, it does have three maxima in it. That region must contain the symmetric and asymmetric methylene group stretches, as well as the symmetric methyl group stretch. Upon forming the ethoxide, of course the OH stretches no longer present. In blue, we can identify the asymmetric methyl group stretch. And then in orange, what I need to convince you is the methylene group, symmetric methylene group stretch and nothing else. Interestingly, here in the skeletal stretch modes, you find that the symmetric CCO stretch has gotten stronger with respect to the asymmetric CCO stretch in the ethoxide as opposed to the ethanol. In order to get a real idea of the orientation, though, we've used the range of deuterated ethanols to form deuterated ethoxides. Showing here the region between 2,000 and 3,200 wave numbers, which contain at its high frequency end the CH stretches and at its low frequency end the CD stretches. The top spectra is the spectra you saw at the bottom of the previous overhead, where we've identified the asymmetric methyl group stretch and the symmetric methylene group stretch. If you deuterate the methylene group, then in the CH stretch region you can still identify, of course, the asymmetric methyl group stretch. But it's not unambiguously clear that that's the only mode present, because at that asterisk there is a combination band of two lower frequency deformation modes. In the CD stretch region, we can identify the symmetric methylene group stretch, and now here in purple we can just make out the asymmetric methylene group stretch as well. If you deuterate the methyl group, then in the CH stretch region we have the symmetric methylene group stretch, and now we can identify, having moved the methyl group out of the way, the asymmetric methylene group stretch as well. In the CD stretch region, just the asymmetric methyl group stretch. If you fully deuterate this species, then you can find all three modes we've identified, both the symmetric and asymmetric methylene group stretch and the asymmetric methyl group stretch. There is the apparent absence of any strong intensity from the symmetric methyl group stretch. The transition dipole moment for that mode lies along the C3b axis of the methyl group, which is coincident with the carbon-carbon bond. So its absence would tend to indicate, according to the selection rule, that the carbon-carbon bond of the ethoxide is roughly parallel with the surface, that is, that the methyl group lies down. The presence of the asymmetric methylene group indicates that the plane of the species, as defined by the CCO atoms, is tilted with respect to the surface in order to give rise to some projection of the asymmetric transition dipole moment back along the surface normally. And that's what's try to indicate here the structure of ethoxide. The interesting thing is I didn't have to make that myself. That's from Yates's group. That's their structure for ethoxy on the nickel 111 surface. What's interesting about that is that we agree in general about the structure of ethoxide on these two surfaces. It's the same face, the 111 face, but ethoxide is formed in very different ways on copper and on nickel. On copper, it requires the reaction with the pre-oxidized surface. On nickel, ethoxide formation goes just by OH bond scission as a function of temperature. And in fact, the population of ethoxide on the nickel surface is in competition with the desorption of the alcohol. When we looked a little closer, though, we decided we could figure out a little bit more than that. The spectra you saw before for the multilayer and ethoxide spectra. First, the region where you expect to find the symmetric methyl group stretch, in that region the intensity is not zero. So there may be some intensity from the symmetric group there. But even more importantly, here in red and in blue, you find that you can identify the symmetric methyl group deformation mode, whose transition dipole moment behaves in exactly the same way as the stretch. So its presence indicates that the carbon-carbon bond is not exactly parallel with the surface. It is tilted away, and the relative ratios of these things means that we can identify the angle. That's what we've done using the simple model of just a dichroic ratio, so it's not a complex model. But we need, in order to describe the orientation of ethoxide, we need two angles. You need a methyl tilt angle, the angle between the carbon-carbon bond and the surface parallel, which we describe as theta, and you need a molecular tilt angle, phi, which is the angle between the plane of the molecule, as defined by the CCO atoms, and the plane of the surface perpendicular. For each modal group, then you'll get one piece of data, the normalized intensity ratios. And what we found through rotation of axes is the expression for the projections along the surface normal in terms of these angles theta and phi, and the projections of the transition dipole moments with respect to the XYZ molecular axes. So for each data point, you will have one equation and two unknowns. You'll need more than one piece of data in order to determine where the solution sets converge. Here I'm showing the results from some of our best data sets, as we can pick and choose among the data sets to find the best data sets. And they're the ones you might expect, really. The two best are on top here. From the deformation mode in CH3CD2 ethoxide, normalized with respect to its gas phase intensities, the set of angles theta and phi, and also from the methylene group stretches from CD3CH2 ethoxide, again in this case normalized with respect to its gas phase intensities. You find that the solutions converge for a methyl group tilt of about 30 degrees and a molecular tilt of about 15 degrees. I was interested myself in determining whether or not the use of multi-layer intensities for the normalization would make much difference. In order, if you believe that the gas phase intensities are the right way to go, in other words, what I'm asking is, if you used multi-layer, what is the measure of the true randomness in multi-layer? And I've shown here for this same data set, the methylene group stretches from CD3CH2 ethoxide, in this case normalized with their multi-layer intensities. You find that it converges in the same spot, 15 and about 30 degrees. The error is not great for using multi-layer data. It's still difficult to picture this, and I really need a three-dimensional model of something that I can point out. But what I'm saying is that the angle between the carbon-carbon bond and the surface parallel, that angle theta, is about 30 degrees. The angle between the plane of this molecule, as defined by the CCO atoms, and the plane perpendicular to the surface, phi, is about 15 degrees. And the angle many people are interested in, the angle between the carbon-oxygen bond and the surface normal, if you do the solid geometry, that angle is about 18 degrees. We also then did trifluoroethanol and trifluoroethoxide, where we replaced the methylene group with a trifluoromethylene group. here for the multilayer and for trifluoroethoxide. You can see that in the multilayer we can still identify here in green and red the symmetric and asymmetric CCO modes. And now it's, for the methyl group, it's much easier to find them, CF being such a strong dipole. We can identify the symmetric and asymmetric methyl CF3 stretches. In the higher frequency region, we have the OH stretch. Upon forming trifluoroethoxide, in the higher frequency region, although it's quite weak, you can see that we can identify both the symmetric and asymmetric methylene group stretches. Again, this species is going to be tilted, molecularly tilted on average for the IR spectrum. In the skeletal stretch modes, the first indication that the orientation of this species is not the same as ethoxide is that the loss of intensity, the lessening of intensity of the symmetric as opposed to the asymmetric CCO stretch. This is the opposite of what we found in the case of ethoxide. But it's even more clear when we realize that the symmetric mode is now even the strongest absorption in the spectrum, and we can identify both the symmetric and asymmetric modes. You can see that the asymmetric modes, their degeneracy has been lifted by interactions on the surface. You can't quite do the kind of analysis we did for ethoxide here. We don't have quite the data set. But we can use the intensity ratios of the methyl trifluoromethyl group in order to determine the angle, which is its equivalent to the angle theta in the ethoxide. And we find when we do that, that now the angle theta, the angle between the carbon-carbon bond and the surface normal, is about 33 degrees. This group is tilted up and away from the surface. If you do the solid geometry for this species, then the angle between the carbon-oxygen bond and the surface normal is about 37 degrees. I'd like to thank our postdoc now, Dr. Amy DePaul, for discussions on the nature of these modes, and my fellow workers, Jerry Myers and Chris McFadden. This work is funded by the Air Force.
Well, thank you for a very nice job. Let me just quickly, I'm curious. In the ethoxide structure on there are a pretty fair number of normal modes.
Yes.
How many do you know, how many normal modes total are there for that, and how many of them now have you pinned down for that adsorbed molecule?
The numbers sticks in my head is either 19 or 24, and I can't remember which one it is.
For the total number?
For the total number,
yeah.
In ethanol. And the modes that exist on the surface are all except anything associated with the OH.
Yeah, right, of course.
And also, you find that some of the out-of-plane, you can identify here in the weak modes in the skeletal group, you can identify the out-of-plane methyl group rock, and it's not present in the ethoxide.
But this sounds like maybe you've got better than 90% of the normal modes you have identified on there and done well enough to have done isotope shifts and so on.
That's
so
right.
That you're sure you know what you're, yeah.
We're pretty
I find
sure
that that's pretty impressive, I think.
It just happens that this thing is tilted in such a way, the average structure of this thing has both a tilt for the methyl group and a tilt for the whole molecule. That's going to give rise to projections from all sorts of modes.
Norman, you had...
Yes, I just want to address myself to the question of whether the plane containing the CCO is perpendicular to the surface or not. You suggested tilted, but as I understood it, your suggestion was based on the fact that you measured a weak asymmetric CH2 strength, which should be forbidden according to metal surface electricity. Now, in the CH stretching region, it is well known there are problems because of Fermi resonance with overtones of deformation.
That's right.
The only comment I would like to make is that a better proof of that would be to check whether or not the CH2 rock or the outer plane CH3 rock are truly missing or
They are missing to the limit of our ability to detect them.
Right. Well,
so you could do an error analysis where you assume that it had that intensity up to your limit of your ability to detect them. In fact, I did that kind of analysis in a way. In one part, I did, when I was doing the analysis, let's use the next one. When I did the analysis, I used, in one case, data from CH3, CH2 ethoxide, where we know that the region of the symmetric methyl group stretch has also in it the asymmetric methylene group stretch. But I assumed that all the intensity in that region was from the symmetric methyl group stretch, and I gave it a full width at half maximum of the asymmetric mode. And I determined the maximum error in theta you could get. And that, you see that error is not great. It's less than 5 degrees in theta. So I don't know what the consequent error would be in phi for the methylene. That's true.
The other questions? For this. Well, thank you for a very impressive job. We have a few